Hi everybody, so this is the follow-up to the RC circuit tutorial. We're going to do a example problem. Okay, so let's jump right into it. We have a capacitor, a simple 1 farad capacitor. I'm going to put it with a 15 ohm resistor. So one of the key things from the previous tutorial is we want to get an idea how much time it takes to discharge a certain amount, complete amount, whatever. And we introduced this concept of tau, the time constant, which is the product of resistance times capacitance. It's actually a very good problem for you to prove that an ohm times a farad is actually equal to a second. If you go back to the equation where we said that, something after a certain time is equal to, let's say it's charge after a certain amount of time, is equal to a fraction of the original, and that's negative t over RC. From a mathematical standpoint, it makes sense that RC has to have units of time, such that time units divided by time units gives us a number, because you can't raise something to a power that's not a number. You can't raise it to something that has units. That does not make sense mathematically. So there's another justification that R times C has to have units of time. So in order to figure out how things are going to charge or discharge, is we do tau, which is R times C, and that's going to be simply 15 times 1, or 15 seconds. That does not mean that it's going to take 15 seconds to charge it. That's going to be after one iteration, which is going to be equal to the natural log of 2 times the original. So if you go back to the chart, completely charging it is about 5 taus. And 5 taus would therefore be about 75 seconds. So that's one way you can look at it, and how we know when it's completely charged. Okay, so if you were charging this, what would you have? Well, if it's a light bulb, you might say when it goes out, but let's say the resistor is not a light bulb. So assuming you have a voltmeter there, then you would say that when the voltage across the capacitor is equal to the EMF. Technically, it would be a negative value to that. Okay, if you had so that's with a voltmeter. Whoops. Alignment's off on this. And if you had an ammeter, then you would look for when the current becomes 0. Okay, now we want to predict okay, so now we've fully charged it. And note that we don't have the same equation for charge. I didn't think I brought this up, but the equation for charging is slightly different for the equation for discharging. Discharging, we might say any quantity, V or Q or I, equals this e to the negative T over RC, if this is for discharge. For charging, it takes on a slightly different value. It's V equals 1 minus, okay, and you don't have to know this. This is not part of the AP curriculum. It's part of the the IB curriculum, but it would become more like that. But we don't ever have to use that. That's why I'm using this 5 taus type thing. So when we're talking about charging, you want to think in terms of 5 time constants to get to about greater than 99%. For discharging, then we're going to use the equation. So we have a fully charged thing. We're predicting how much time it will take for the potential difference across to be half the original value. So we're starting at some V, and we want to go to half of that. So that implies that we're discharging. So how do we set that up? Well, we're looking at voltage. So we're going to say our voltage at some time is equal to our original voltage, e to the negative t all over RC. Okay, we know what R and C are. What are we trying to solve for here? So you have to interpret this statement right here, half the original value. And if you understand that, what you're basically saying is V over V naught is 0.5, right? So my new value divided by my original is 50%. So if I rearrange this equation, I would say V over V naught equals e to the negative t over RC, which we now know is 0.5. So now I know what to solve for. I'm solving for t, and so in order to do that, I just got to do a little exponential. So I'm going to take the natural log of both sides, and that the left side becomes negative t over RC equals the natural log of 0.5. Okay, if I'm going to solve for t, then I'm going to do it all algebraically before I plug in any numbers. So I would say negative natural log of 0.5. That's important because a natural log of 0.5 is going to be a negative number, and negative and negative is going to be a positive, which I need to have in order to get a time. I can't have a negative time. Let me see if I'm doing this right. Not divided by RC, but multiplied by RC. So let me rewrite that. So that's going to be negative natural log of 0.5 times RC. Okay, so the natural log of 0.5, if I plug that in, got my handy calculator here. Let's see if it's been a long time since I've done that. Whoops, did the wrong, oops, pressing all the wrong buttons. Ay caramba, how do I get out of this? Clear, there we go. Log of 0.5. All right, so I get 0.69, so I'm going to have negative of the negative, so 0.69 times 15. Remember RC, we already calculated above, so multiply those together, and I get about 10.4 seconds. So we know to fully discharge is going to be about 5 taus or 75 seconds. So charging it is going to be 5 taus. Discharging it is also 5 taus. So 75 seconds to fully discharge it. To get to half, we only need to go 10 seconds. So most of the discharging occurs early on, and then it tapers off dramatically. So that's what that graph is telling us. We get a big steep drop here. Afterwards, the drop is less dramatic. So that answer is consistent. Now, how many time constants is this referred to? Well, that's fairly straightforward. 1 tau, we already know, is 15 seconds. So we have 10.4 divided by 15 seconds, and that's going to be roughly 0.67 taus. So not even one full time constant there. Okay, now the last thing I'm going to talk about, we didn't do in lab because we were pressed for time, is what if you put a capacitor in parallel with the resistor. So I have a schematic here where we have a voltage source, a capacitor in parallel with it. You're not going to have to do any calculations per se. And this is definitely IB, but this is also AP, right? AP wants us to know this. AP doesn't expect us to know the equations, but expects us to know how things behave descriptively in terms of current voltage for series and for parallel. Okay, so we're going to close this switch. What's going to happen? Now, this is a very subtle thing. You have 2 branches. And you might think, all right, you're going to get current flowing through the capacitance branch and current flowing through the resistance branch, which are independent of each other. However, we have to recall the little factoid that when a capacitor is uncharged, its initial resistance, R0, is essentially 0. So when the switch is closed, the initial voltage drop across R is going to be 0. This is not going to get anything because we essentially have a short circuit here for a very, very brief period of time. In other words, a brief period of time corresponding when that capacitor is essentially not charged or charged with a very small amount. And therefore, no current flows through it. So that's weird. Even if this is a light bulb and you close this switch, this light bulb initially would not turn on. Okay, now after some time, again based on the value of tau, which is RC, okay, the current through the capacitor becomes less. We know that as the capacitor gets charged, current through it is going to get less and less, and then through R. Okay, so in other words, as this becomes charged, right, this would be positive, positive, negative, negative, and it gets towards full charge, but not necessarily quite, then this resistance, in a sense, stabilizes, and this is going to be a parallel circuit, and it's going to get constant current. And in fact, after some time of 5 RCs, this branch is going to have infinite resistance, and you get no more current down here. But that's not going to affect the other resistor, the parallel branch. The parallel branch is only affected when the other branches have 0 resistance and creates a short of sorts. All right, lastly, now what happens if we open the switch back up? Remember, this is charged. Positive here, negative here. I open this up, well, I still have a loop right there. Okay, so you want to make sure you recognize the opening switch will cause a capacitor to discharge through R, as seen by that, and then we could talk about how much time to discharge, etc., and we're back to that time constant and the exponential equation. So, as always, come in with any questions. Hopefully, both those examples help clarify anything that you might have been questioning.